you guys have been working with composite functions forever. It just maybe nobody told you you were working with composite functions. So here's a simple example. So obviously, if you're selling something, like let's say sales at a for merchandise, food, whatever, at a local baseball game, that depends on how many people come to the game. And so let's say for every person that comes to the game, you make $15 in sales off various things. And so the sales is equal to 15 times that. So the sales depends on the number of people that come. But the number of people that come would depend on how much you charge for a ticket to the game. And so the ticket sales, the number of people that come to the game, depends on your ticket price according to this function. So essentially, as you increase P and divide by a bigger number, the number of people that come goes down, and then you make less money. So sales is a function, S is a function of N, but N is a function of P. This is kind of like a composite function. It's a function like of a function. So let's just play around with this simple example for a sec. Nothing crazy here. So if the ticket price is $10, what kind of sales could we expect? So we can hammer this out. This is just kind of plug and play, like formula stuff from maybe grade 9 or something. So ticket price is $10. So when P equals 10, then N equals 1,000 divided by 10. So N equals 100. So 100 tickets sold. It is a local baseball game. 100 tickets sold. Okay, now that we know N, now we can find the sales. So when N equals 10, when N equals 100, then the sales is equal to 15 times 100. Like nothing crazy is going on here, but it's an example of a function of a function. And so 1,500 in sales. So this was an example of a composite function. Revenue is a function of sales. Ticket sales is a function of price. It's a function of a function. So here's another example. This one's just like a generalized example. None of X, Y, and U have some immediate context, but it's kind of similar. So let's determine the value of Y when X equals 5. If Y is equal to U squared plus 1, and U is equal to 2X minus 3. Now I'm going to show you guys kind of two ways to do this. Maybe we can go at it together the first way that we did up above. So maybe you guys can do that. When X equals 5, U equals whatever. And then once you have that value of U, you guys can find the value of Y. I'm going to do my attendance while you guys do that, and then I'll show you a second method. Make sure I pause my recording. All right, let me play catch up here. So X equals 5, U is 2 times 5 minus 3, so that's equal to 7. And then when U is equal to 7, then Y is equal to 7 squared plus 1, 49 and 1. You guys get 50? That's one way to do it. Here's another way we could do it. Or, if Y is equal to U squared plus 1, and we know that U is equal to 2X minus 3, we could just make Y as a function of X and then just have to kind of skip the middleman. So if we take Y equals U squared plus 1, U is equal to 2X minus 3. We could just replace U with 2X minus 3 squared plus 1. And now we have Y directly as a function of X. You want to know the value of Y when X equals 5? Well, now you're just back in grade 10. That's kind of like a quadratic expression. Just plug in X equals 5. And I'll do that off to the side here. But yeah, you can see we're just going to get the exact same answer. Because we're going to have 2 times 5 minus 3. And we're going to square that, and then we're going to add 1. It's essentially the same math we did before. It's just we're putting it all in one function. So what 10 minus 3, 49, Y equals 50. So two ways, one at a time, or just make one single function, Y as a function of X. You guys convinced? Same answer both ways? Okay, let's take this one step further. So this might have been an exercise that you did in your grade 11 course, but it might not have been. Everybody should be able to do A and B. You have two functions. You're just asked to evaluate a function at a specific value. So we can just do those together. So this is no problem. You guys were introduced to function notation in grade 11. F at negative 3 just means sub in minus 3 for x into the function f. That would just be 9. And g at 15, well, we have our function g saying plug 15 into that. 15 plus 1 is equal to 16. What we can actually do as well is we can not just plug in a specific number into a function, we can actually evaluate a function at another function. We can replace x with not just a number, but an entirely other function. So check out C. This might be some new tech for you guys, some new notation. But what this, how you could read this, you could read this as f of g of x. It's like a function of a function. It's a composite function. How do you evaluate something like that? Well, just like you did in A. Evaluating f at minus 3, you just plug minus 3 into the function. F of g of x, well, where you see an x in the function, instead, you just plug in g of x. So where in A, we squared negative 3, in C, we're going to square g of x. And the function g is x plus 1. It's a function of a function. And as you can see, when it comes out in the wash, it's just x plus 1 squared. Let's try one more together, and then I'll just do a little aside, just convincing you guys you've already been working with composite functions already in this course. We just haven't called it that. So g of f of x. Well, to do g at 15, what we did was we just took 15 and plugged it in g, and you add 1 to it. So if you're evaluating g of f of x, well, you just add 1 to f of x. You just replace x with f of x in that function g. And what's f of x? F of x is just equal to x squared plus 1. Function of a function. If you guys, hopefully you guys recall, but when we set up the definition of the derivative, I can write today. You guys were essentially doing this when you did f of x plus h. You're plugging a function into another function. Back in grade 11, grade 12, when you did transformations, so you might remember something that looked like this, when you guys talked about vertical shifts and all that stuff. This is composite function stuff too. It's just you guys never called it composite functions. We're just now introducing that term. So life is good. You guys have already been doing this stuff. Everything's okay. Just a side note, a different notation you might see maybe in next year's math course or whatever. F of g of x is sometimes written this way as f with like an open dot g in brackets like that. So it doesn't say fog. That's open dot. It's like a symbol that means compose of x, kind of like that. And g of f of x would be g composed f. So it's not goff. It looks like that. It's g composed of f. So the way you would read that is you would read that as f compose g of x. So just while I give around the next thing, here's a little exercise. Can you guys identify, and I've given you the composite function. Can you identify the outer function f and the inner function g, what we plugged into that function f. So here's, maybe I'll do the first one, then pass things out. So here's a function h, x minus 2 cubed. There's an inner function there, and there's an outer function that we plugged it into. Does any brave soul think they see what maybe the inner function is probably easier? Charlie, see the inner one?
X minus 2.
Yeah, x minus 2 is the inner function. And did you see the outer function as well? Yeah, exactly. So for that composite function, you've taken x minus 2 and you've plugged it into x cubed. Perfect. Later on in the course, we're going to find derivatives, make graphs of interesting composite functions like those last two. So can you guys give those a try while I pass on the next thing? I'm not going to pause the video because the risk of me forgetting to unpause is too great. So we'll just pass on the next thing. Now I don't want to hear, that's 3 pages. We're doing this over 2 days. So actually I'm only giving you part 1. Never mind. Just ignore what I just said. I thought I printed off both pages, or both packages. We'll do it. You're welcome. All right, I saw a lot of right answers walking around from people that don't normally participate. So this could be a good time. Bring that initiative learning skill from a G to an E. How about part B? Inner function. Maybe let's do inner function first and outer function second. Kara, go ahead.
G of x equals x squared.
Yep. What's the outer function?
B sine x.
Yeah, good. Yeah, it's like you plugged x squared into sine x instead of like an angle or something like that. Great. And how about the last one? A little bit of a step up on the last one. Eugenia, go ahead. That's the outer function. Yeah, it's like you took the exponential function 2 to the power of x and you plugged in the log function. All right, look at you guys. Very good. But yeah, like hopefully these exercises just make today go a bit more smooth. And hopefully you're also kind of convinced that you have been working with composite functions for quite a while now. We just haven't called them that. All right. Anything you guys want to chat about? Anything on your mind before we move ahead? All right. So before we begin, can you guys find the derivative of these two functions? So I'll give you a hint. You are going to be using the power of a function rule. I guess it's not much of a hint. It says that right down there below. But yes, give those two a go. Because some more good news. Today's lesson is called the chain rule. And you might be thinking, oh my God, another rule. But actually, you guys have already been using this rule. A specific example of this rule. All right, I'm going to come along for the ride here. Let's try deep purple, just to mix things up today. All right, so power of a function rule. Bring down the 9, leave the inside alone. Take 1 off the exponent with 1 additional step, multiplied by the derivative of what's on the inside, which would be 21x squared, minus 8x plus 3. I think that's okay. Notice though, and you guys have done many derivatives, like literally you've done 23 of those combined with all the practice you've done. Is this just not a composite function? There's an inner function and there's an outer function, right? The inner function is this cubic polynomial, and the outer function is x to the power of 9. This is a composite function. Let's just jot that down. And my point here is that you guys have already been finding derivatives of composite functions when you've been using this rule. In this question, the outer function is, I'll just use y equals notation, y equals x to the power of 9, and the inner function is this cubic 7x cubed minus 4x squared plus 3x minus 2. It's a composite function. And again, you guys have already been taking derivatives of composite functions. Now we're just calling them composite functions. Life is good. Can you guys try the next one? I'll give you the starting point. Well, I guess you could use the quotient rule. My personal preference for a function like this, because I can easily write it as a power, my personal preference is to write it as a power. If you've already done the quotient rule, our answers should match up. I'll mix in some Leibniz notation here, just to keep you guys on your toes. All right, so bring down the exponent, minus 8. Leave the inner function alone. Notice I called it inner function. Minus 5, and then the derivative of the inside is 1. I'll still multiply by 1 there. And that's it. Minus 8 over x minus 5 to the power of 5. Look, here's another composite function. Inner function, x minus 5. Outer function, 2x to the power of minus 4. You guys convinced you've already been doing derivatives of composite functions? Yeah. So what have we been doing the lesson for today? I don't know. We gotta introduce this generalized rule for doing composite functions, because later on we're going to want to find derivatives of these kinds of functions as well. So this is just the point in the course where we introduce this general rule, even though you guys have already had experience using it. So let's continue. I'm going to now tell you guys the generalized chain rule. I'm going to give it to you guys here. We're going to state it in words. We're going to take it for a spin. And then hopefully by the end of the day, you guys are just like, okay, I've already been doing this, so I get it. All right, here's what the chain rule says in function notation. So if you have a function, I'm going to call it, please forgive me, I'm going to use the same notation I did when I wrote this out earlier. Apologies if you take your notes in pen. If f of x is equal to g composed of a function h of x. So if you have a function that's a composite function, how do you find the derivative? So we're gonna write this out. We're gonna put it in words, and we're gonna give it a spin. But it might take a second to digest. But let's jot it down first. Then the derivative of f. How do you find the derivative? What you do is you take the derivative of g, so g prime, but instead of g prime at x, it's g prime at h of x. You leave the inner function alone. So g prime at h of x. And then you multiply by the derivative of what's on the inside. So that might look like some new tech for you guys, but you really have already been doing this. You've been taking the derivative of power functions by bringing down the exponent, leaving the inside alone. Can you guys add this note here? We want to leave the inside alone. And then you multiply by the derivative of what's on the inside. Now, I'm going to put this in words so that maybe if you like to have, and I certainly do, when I'm taking derivatives, I kind of have a mantra that I say in my head, and then when I teach it with you guys, I say it out loud. But in words, why won't you work? Get out of here. I can't pick something bigger than 20. We're going to do 20, I guess. Inwards, the derivative of a composite function, hashtag 60 words per minute, is the product of the derivative of the outer function. So you take the derivative of the outer function, evaluated at the inner, which is a fancy way of saying you take the derivative of the outer function, but you leave the inside alone, and the derivative of the inner function. You multiply by the derivative of what's on the inside. So let's put that into practice with a composite function. This is a function you guys could already find the derivative of before today. It's just we're reframing it as in this generalized chain rule so that when we encounter more complex functions later on, we have this in our toolbox. But as you guys will see, we just get the same derivative we expect. As a little exercise, can you guys identify the outer function and the inner function real quick? Somebody who hasn't helped out yet today? Got the outer function, got the inner function for us? Or Tiza?
X to the power 4.
Is the outer function? Yep.
And inner is 3x minus 5.
Perfect. Yep, we've just plugged 3x minus 5 into that power function. X to the power of 4. All right, there's g and there's h. Those are two functions. They're not too complex. Let's find each individual piece of this chain rule. So the chain rule says you differentiate g, which is no problem. The derivative of x to the power of 4 is 4x cubed. But the chain rule says the derivative of this composite function is the derivative of the outer function evaluated at the inner. So we take the derivative 4x cubed, and where there's an x, we put in the inner function 3x minus 5 to the power of 3. That's the derivative evaluated at that inner function. And then h prime at x is exactly 3. So if we take the chain rule and just plug in the stuff here, what do we get? G prime at h of x, we just found, is 4 times 3x minus 5 cubed times h prime of x, which is just 3. Now, if you will, just imagine we're in class 2 days ago, and I asked you guys to find the derivative of 3x minus 5 to the power of 4. What would you do? You'd bring down the 4, you'd leave the inside alone, you'd take 1 off the exponent, and you multiply by the derivative of the inside, which is 3. Is that not exactly what we would have done several days ago? Right. It's just, at this point in the course, we have to extend this idea to all kinds of functions so that later on in the course we have it in our toolbox. But in this unit, I will never ask you guys to take the derivative of a composite function that isn't a power function. We're just doing power functions. But we're hopefully just getting used to this idea of the chain rule so that later on it's not too big of a shock. So there's the derivative. We should probably just clean that up. 4 times 3 is 12. But we did it. We did our first example where we just kind of used the definition of the chain rule. But we just saw it's just the power rule, power function rule. Let's do another one. So here we have the function, the root of 4 minus x squared. So let's talk about inner function and outer function. So the inner function, often easier to start with that, 4 minus x squared, just quadratic. And the outer function is root x. We've plugged 4 minus x squared into root x. For finding the derivatives, I'll write that as a power, x to the power of a half. And then let's use the chain rule again, the definition of the chain rule, and then we'll just have a team talk and just realize, oh, hey, this is just the power of a function rule we've been using. All right, so if g is x to the power of a half, g prime of x is 1/2 x to the power of minus 1/2. And then g prime evaluated at that inner function, it's just that derivative, so it's 1/2, but instead of x, 4 minus x squared to the power of minus 1/2. I think I can zoom in a tad. Yeah, that's okay. And then the derivative h prime minus 2x. Putting those things together, the chain rule says the derivative of that function is the derivative of the outer function evaluated at the inner. We have that. It's 1/2 4 minus x squared to the power of minus 1/2 multiplied by the derivative of the inner function, minus 2x. That's the derivative. And then I know I sound like a broken record. That's just how calculus is when we're applying derivative rules. And I chant my mantra every time. If this was you guys several days ago, and you had the function root of 4 minus x squared, which just means 4 minus x squared to the power of a half, what would you do? You would bring down the half. You would leave the inside alone. You would take 1 off the exponent, done, and you would multiply by the derivative of what's on the inside. It's just the power of a function rule, just more generalized. All right. I think I've said that enough. Let's clean this up, and then let's just start doing a few more examples applying the chain rule. So how can we clean this up? A half times 2 is 1, and we just have negative x, and then all the stuff with the minus exponent, the negative exponent would just go on the bottom. It would be 4 minus x squared to the power of a half. Which I'm totally okay with, but if you are looking in your solutions manual, they're going to write it as a root. But I personally don't care as long as there's no negative exponents. All right, let's combine some rules together and do a question that we normally do every time we kind of learn a new rule. Let's find the equation of another tangent line. Now, I have given you guys a graph of the function here. I haven't exactly given you guys the y value though. So this is one where we can't eyeball it. We're going to have to use the function. It looks like 0.5. It looks like something like right there. So let's start just maybe off to the side where you guys have some space. Lots of space here. I'm just going to tuck this in. Where did I do it earlier? I did it over here. So let's just quickly find when x is equal to 0.5. Let's just find f at 0.5. And then we know what our point of tangency is. So what is that? 3 times 0.5 times 1 minus 0.5 is also 0.5. And then we're squaring that. That should be 0.375, but I'll let you guys do it. That's a risky level of mental math for this early in the morning for me. It seems to fit the graph though, right? Yeah, okay, I see some nuts. Let's add that to our graph. So 0.5, 0.375, and then as should be a good habit, let's rough in the tangent line and just to make a prediction. So it looks like we're on the other side of that little local maximum. So it looks like the tangent line will have slightly negative slope. And as we go back, it looks like the y-intercept will be close to 1. I'm just going to do a dashed line here for my tangent line. It's something like that. So we just know what to expect. All right. Now, as we've talked about, finding derivatives, often many different rules apply, and there's many different strategies. I would say this one would not be too bad for you to just expand and simplify. Do 1 minus x squared and then multiply everything by 3x. But I'd like to combine some rules and give our chain rule a spin. So let's work this out. So what's the derivative of f? Well, we have a product of two functions, right? We've got 3x and we've got 1 minus x squared. So let's use our product rule to start. We differentiate the first function, 3, and then leave the second, 1 minus x squared, plus, we'll leave the first function, 3x, and now let's use our chain rule, just the power of a function rule. We're taking the derivative of 1 minus x squared. So we bring down the 2. We leave the inside alone. That's what the chain rule says. We take 1 off the exponent, 1, and we multiply by the derivative of what's on the inside, negative 1. And we should clean that up so we can plug in. Now, if you guys remember that last question on the quiz where plugging in 1 right away was probably more efficient, like maybe you're better than me at this. I don't want to plug 0.5 in here. It looks way too messy for my taste. So I'm going to expand and simplify this all out. You could just plug in 0.5. That's no problem. For me, my brain can't handle that this morning. So 1 minus x squared would be 1 minus 2x plus x squared. And then what do we have? We have 3x and 2 and minus 1. That's minus 6x times 1 minus x. And then we can just do the distributive law and collect some like terms. Plus 3x squared minus 6x plus 6x squared. You guys are doing great today. We've done a lot of stuff today. So what does that give us? 9x squared minus 12x plus 3. All right. That I can handle plugging 0.5 into this morning. And then remember, guys, from our graph, it looks like we should get something negative, but not too big of a negative number. So the slope of our tangent line is just f prime at 0.5. Yeah, fingers crossed. Hopefully this works out. I do this question once a year. Okay, so I'm just going to use my calculator to do all that at once. So that would be 2.25, 9 times 0.5 squared, minus 6 plus 3, negative 0.75. That seems to fit pretty good. Negative 0.75. Oh yeah, it looks bang on. Do you guys get that too? Yeah, perfect. All right, and then it's y equals mx plus b time. And we'll plug in our point. All of our decimals are exact here, so it's really no issue just to plug in the decimals. I forgot my x. Why don't you guys tell me? 0.75 times 0.5 plus b. And it should give us something around positive 1. Maybe not exactly positive 1, but something close to that. Well, that would just be negative 0.375 as well. And we'll add that on. Yeah, 0.75 seems to fit pretty good. So we did it. The equation of our tangent line, negative 0.75x plus 0.75. I'll put a box around that. Now, guys, you could have done that question before today. It's just now we have this generalized chain rule in our back pocket for later. This question is just big. I could have put this question into the power of a function lesson from several days ago. But it was I won't call that an easy derivative. We had to tie in the product rule and the power of a function rule. Anything you guys want to chat about? All right. I've got one more problem for us to do. More of an application problem. So a question where, the diagram's not given to you guys. You have to kind of frame the problem yourself. You have to actually come up with an equation to work with by yourself. Of course, I will coach you guys through this one. So here we have Andrew and David both leave their houses at 7 a.m. for a Sunday run, but they live far. What was that the door? But they live far apart. Andrew's house is 22 kilometers south of David's house. We have a lot of space here. I'm going to do this diagram on the far right here. So David's house, I'll mark with a D, and then who's the other guy? Andrew. Andrew's house, way down here, I'll mark with an A. I'm going to zoom out a little bit so I can get everything in there. All right, so Andrew's house, 22 kilometers south of David's house. Andrew runs north at 9 kilometers per hour, and David runs west at 7 kilometers per hour. So I'm going to put a little arrow here. Andrew runs that way at a certain speed, and David runs that way at a certain speed. So the idea here is, so would you guys agree they start 22 kilometers apart? But as they start their run, they're no longer going to be 22 kilometers apart. The distance between them is going to be constantly changing. And we're asked to find how is that distance changing after an hour. Are they getting closer together? Are they getting farther apart after 1 hour? So to do that, we need to come up with an expression for the distance between our two friends. So from our diagram here, if you assume Andrew runs north for a bit and David runs west for a little bit, then David might be here and Andrew might be here, and we're interested in finding the distance between them. I'm going to use S of t just to be consistent with the second derivative lesson we did. We need to get an expression for that distance. So how are we going to do that? Well, we're going to use Pythagorean theorem. If David runs at 7 kilometers per hour, would you guys agree that an expression for how far he's run would just be 7 times t? Like 1 hour, 7 kilometers, 2 hours, 14 kilometers. You guys okay with that? That's just distance equals speed times time. And in the same way, we can do that for Andrew. He just runs at 9 kilometers per hour. So 9t would be an expression for how far he's ran from his house. If we had an expression for this final side in this right angle triangle, we could get an expression for the distance using Pythagorean theorem. And we can, because remember that Andrew and David's houses are 22 kilometers apart. So if Andrew runs 9t kilometers, then the remaining distance to David's house would be 22 kilometers minus 9t. So then you can just let that digest for a moment. Like if, let's say Andrew runs for 2 hours, that'd be 18 kilometers. And that would mean 22 minus 18, only 4 kilometers left to David's house. You guys okay with that setup there? All right, so now we're ready to go ahead and solve the problem. We're going to use Pythagorean theorem. The distance between our two friends, using Pythagorean theorem, is just the root of the two legs squared. 7t all squared and 22 minus 9t all squared. And what all we use there is Pythagorean theorem. Hypotenuse is equal to the root of a squared plus b squared. Just Pythagorean theorem. Now we're going to clean this up a little bit, but this is just a power function that you guys can find the derivative of. Let's not do that yet. Let's just clean things up a little bit. So I love this question. It ties in so many algebra skills from earlier grades, like 7t squared. Isn't 7t squared? It's 49t squared, because it's 7t times 7t. And then we have to expand this perfect square trinomial, which I'm doing with my grade 11s, recognizing that perfect square trinomial pattern. So 22 squared. I don't personally know 22 squared. 484. And then we're going to have 22 times negative 9t, and then double that. 22 times 9 times 2. So minus 396 times t.
And then minus 9t times minus 9t, 81t squared. And then I'm going to do two things here. Instead of writing it as a root, I'm going to write it as a power of 1/2. And I'm going to collect my like terms. 49 and 81 make 130. So now we have an expression for the distance between them. Now you guys can find the derivative, the rate of change, and then you can find the value of that derivative after 1 hour. So can you guys at least give the first step of the first derivative a try? It might not be practical to kind of simplify it, but at least you guys can do the first step using our power of a function rule, which we now know is just the chain rule, a specific application of the chain rule. I'll resist the urge to do this. I'm just going to wait 30 seconds while you guys give the first step a go. I just do the first step. Don't worry about simplifying anything. All right, here I come. Bring down the 1/2. Leave the inside alone, the chain rule says. Take 1 off the exponent, so that's the derivative of the outer function, and then the derivative of the inner function. 2 times 130 is 260, and minus 396. That's our derivative. Now, the goal of this question is to find how fast their distance is changing after 1 hour. So our goal is to find s prime at 1. Guys, here's another situation where, in my opinion, there's no value in doing any simplifying. Let's just plug in 1. So we're going to have a half, and then you can show as much steps as you want. It'll just be 130 minus 396 plus 484 to the power of minus a half, and then 260 minus 396. We're just plugging in 1. That's why I'm basically just dropping the t's. With your display calculators, you could probably do that all at once on your calculators. I am old and don't know how technology works, so I'm just going to do 1 intermediate step. That bracket is 218. I'm just going to keep it as minus 1/2. My calculator can handle that negative exponent. And what's that? Minus 136. All right, and then what's that equal to? Now it's just number crunching. So 218 to the power of negative 0.5 times 1/2, or times 0.5, and then times negative 136. So at the end of the day, I got negative, to 1 decimal place, negative 4.6, and that would be kilometers per hour. You guys get that too? What's negative means they're actually getting the distance between them. They're actually getting closer at this point. They are getting closer together, even though David's running a bit to the west as Andrew chases the north. Yeah, the overall distance between them is getting smaller. So they are getting closer together. And we did it. Great job today, guys. We did a lot in, when did class start? We've done a lot in like 45 minutes. We took up that quiz, we did a warm-up, and then we banged out a pretty intense lesson. You guys did really well. We have recorded this lesson, so you guys have the luxury of going back over things with the dulcet tones of my voice later if you want to. But otherwise, I got some practice for you. And because we did this heavy lifting today, tomorrow I just have a 1-page thing with a couple more examples to do. It'll take 15 minutes, and we'll have a lot of practice time tomorrow, okay? So that's the game plan. Gonna stop the recording.